Hello, CHY 107. And so now in this video, we're going to start to talk about the various types of chemical reactions. And so these categories that we talk about are really sort of a sampling. Many reactions can be classified in this way, but there are other reactions that may be classified differently. But this is going to give us sort of a nice broad overview of how some reactions can be classified. Four basic categories that reactions can fall into are combination reactions, decomposition reactions, single replacement, or double replacement. You may see other names for some of these, by the way. Combination reactions might also be called synthesis reactions. And both of our replacement reactions may also be called single displacement or double displacement. Same thing, just different terminology. Some other classifications that we might see are oxidation reduction reactions, which we will talk about in this video, acid-base reactions, which we will also talk about, and we might talk about some combustion reactions, but then reactions of organic compounds we'll be looking at a little bit later in the course. Many of these types of reactions can also be classified as one of these four different types. It just depends on sort of how we're talking about the reaction and what we want to get out of our discussion. And so that might factor in how we talk about it. Just a little hand lotion gets very dry down here in my basement. So that feels better. Okay, let's move on. So the first type of reaction is a combination reaction. In a combination reaction, two elements and or compounds come together to form one. And so we have the basics of it are that you're going to have two reactants coming together to form a single product. And so in this example here, we have nitrogen plus oxygen. Remember that nitrogen and oxygen are both diatomics. So those are going to come together to form nitrogen monoxide, NO. And again, note the two there for our balancing purposes. Let me bring up, I don't think it is, just bring up our whiteboard here. There's two of me, you certainly don't need that. Oops, gotta plug in my iPad. Sorry, not as organized as I should be right now. Let's do away with that view. One of me is plenty. Let's see if we can do it now. Sorry, should have made sure to have this before I started my video. There it is. So let's just look at how we would put that together, by the way. Actually, in this case, we know it's nitrogen monoxide, so we're talking about the formation of nitrogen monoxide. We know that nitrogen is a diatomic, so that must be N2. Oxygen is also a diatomic, must be O2. We know that we're forming nitrogen monoxide just because that's the reaction we're looking at. So that's going to be NO. And so then we would look to balance it. Our next example, sodium plus chlorine coming together to form sodium chloride. So again, Na plus Cl2. Sodium is not a diatomic, so we would just write it as Na. Cl is a diatomic. When they come together, though, so now we're going to use our rules for forming ionic compounds. Na is a 1 plus, Cl is a 1 minus. That tells me when they come together, the formula must be NaCl. Now I look to balance. 1 Na here, 1 Na here, that's okay. 2 Cls here, only 1 over here. So I'm going to fix that by having 2 NaCls. That gives me 2 Nas, 2 sodiums on my product side. So I fix that with an Na on my reactant side, an extra one. Decomposition reactions, just the opposite. Some compound is going to break apart and split up. And so one reactant splits into two different products. And so we have an example here, a couple examples. We have sodium azide. Azide is just N3 as a -1. That's not something that we had to memorize, so don't worry about that. Just know that that's what it is for this demonstration. But sodium azide is going to split up into sodium and nitrogen. And so NaN3, Na, when we look at our product side, Na is not a diatomic, so that's going to stay as just Na. N2 whoever is, so we're going to get Na plus N2, and then we would have to balance it. Carbonic acid would split up into water and carbon dioxide. Don't worry about how this one splits up, just be able to, because this goes a little, this type of reaction here goes a little bit beyond what we're going to look at for how reactions work in this course. What I do want you to recognize that it is a decomposition reaction. One reactant splits into two products, and that's what a decomposition reaction is. In a single replacement reaction or single displacement, one element substitutes in a compound for another one. And so you can see in this case here, A, whatever element A is, basically comes in and boots out B. So that in the product side, B is now by itself, but A is now in a compound with whatever C was. Let's just look at an example. So here we have magnesium plus HCl, hydrochloric acid. So the magnesium essentially comes in and boots out the hydrogen. And so let's look at how we would actually do that out. Let's look at the whole process here. Let's say that we only knew what our reactants are, and we wanted to figure out the products. So we know that Mg is going to come in and kick out our hydrogen. And we know that it has to be that way because the Mg needs to come together with the Cl because the Cl is a minus charge and the Mg is a positive charge. So we know that Mg has to be kicking out has to be kicking out the H and getting together with the Cl. And so then when we look to figure out our products, we know that the charge on Mg is 2 plus, the charge on Cl is a 1 minus, and so they are going to come together to form MgCl2. Hydrogen has been kicked out and is by itself, but hydrogen is one of our diatomic molecules, and so that's H2. And so then the last thing we have to do, I'm just going to clean this up by getting rid of my arrows here. Last thing we have to do is just balance it. And we can see that putting a 2 in front of our HCl balances this equation for us. Let's look at another example. Let's look at maybe aluminum plus sodium bromide. Again, we know that aluminum is going to come in and kick out the sodium so that aluminum and bromine can come together, a plus minus. Aluminum has a 3 plus charge, bromine has a 1 minus charge. They're going to come together with a formula of AlBr3. Sodium has been kicked out, so that is now by itself. It is not a diatomic. And so then we just have to balance it. We have 3 Brs on our product side, only 1 on our reactant side. We'll fix that with having 3 NaBrs. And we have to switch, then fix the fix our NAs with 3 NAs. In a double displacement reaction, pretty much the same thing, but now we just have 2 compounds essentially that are switching partners. And so here we have AB plus CD. A essentially is going to switch places with C. And so then we're going to have AD plus CB. And so we can see that example here. Here we have potassium iodide plus lead nitrate. The potassium is going to come in, kick out the lead. So then the potassium is going to get together with the nitrate with the resulting chemical formula for when the 2 of those come together, KNO3, a 1 plus and a 1 minus. Again, the importance of knowing your polyatomic ions. So we know that NO3 is going to stay together. PB then comes together with our I, so we get PBI2. Now you might ask yourself, well, how did I know? Because PB is one of ours that could be different charges. How did we know then that it was that it was going to be a +2? We knew because of what it was with. And so we had Ki plus, what do we start with? PbNO3 2. And so when we look to figure out what's going to be coming together with what, we're essentially looking for our new plus minus combinations. And so K we know is a 1 plus, periodic table tells us that. Iodine is a 1 minus. NO3 is our polyatomic ion nitrate. We know that's a 1 minus. There are 2 NO3s. There's only 1 lead. It tells us that lead must be a 2 plus. And so then we look for our new plus minus combinations. K is a plus, NO3 is a minus. So K with its 1 plus, NO3 with its 1 minus. So those are going to come together as K, NO3. Our other plus minus combination, lead and iodine. Lead we figured out is a 2 plus, the I is a 1 minus. So those are going to come together as PbI2. Then our last step is balancing. We see that we have, and I'll just clean this up a little bit for us. And so we can see that we have 1K, 1K, 1I, 2 I's. Let's go ahead and start by fixing that. 2 KIs. Now I have 2 iodines. Or sorry, now I have 2 potassiums. I can fix that with a 2 right here. Now that gives me 2 NO3s, but lo and behold, I had 2 NO3s. And so there's our double displacement reaction. Here's another one down here. And this might be a little bit harder to see until you recognize that another way to write water, another way to write H2O, you could also write it as HOH. So if you think of water as HOH here, then hopefully you can see that this is another double displacement reaction. So that's our 4 basic types. Let's look at some other classifications. In an oxidation reduction reaction, also known as a redox reactions happen all over the place. In some of the processes involved in cellular respiration, producing energy in our cells, some of those processes happen through redox reactions. The energy we get from internal combustion engines, how batteries provide electricity, burning fuels, hydrogen fuel cells, all different examples of redox reactions at work. In a redox reaction, electrons are being transferred around. Some of the elements in the reaction, 1 or more, are losing electrons. And then that means that 1 or more of the elements involved are gaining those electrons. Oxidation and reduction always occur together. If one element is losing electrons, another element is picking them up. There's a couple different ways to remember which is which. One of those ways is just with using the term oil rig. Oxidation is loss. Reduction is gain. Another way, and my personal favorite, and you'll still see me literally writing this sometimes on my papers when I'm working out a redox reaction. Leo the lion goes grrr. It's silly, but get that into your head and you're not going to forget this. Leo goes grrr. Loss, or lose rather. Lose electrons, oxidation. Gain electrons, reduction. Same thing as oil rig. So it's just a different mnemonic and a different way to remember it. And so here's this example here. So we have AgCl plus Cu gives us CuCl2 and Ag. I'm not going to worry about the stoichiometric coefficients for right now for this example. One of the things that we have to recognize here is that an atom in its molecular form, and so something that's when it's by itself in its natural state, its charge is 0, its oxidation state is 0. And so this copper here has an oxidation state, or you can think of it as a charge for now, although it's not really the same thing. We can think of it that way. It's a charge of 0. So does this silver. Let's look at what happens from one side to the other, though. So copper here is a 0. Copper here, we know that Cl is always a -1. Just that's Cl when it's in an ion, as it is here, it's in an ionic formula, is going to have a -1 charge. And there are 2 of them. That means that this copper here must be a 2+. And so this copper had to have lost electrons. Remember, electrons are negatively charged. So this copper had to have lost electrons going from one side to the other. Leo, lose electrons, oxidized. So the copper was oxidized. The silver, on the other hand, Cl with its -1, so the silver as it exists on our reactant side must be a +1 ion. As it goes over to the products, it's now 0 because it's silver in its natural form. And so if it's going from positive to 0, that means it has to be gaining electrons. Electrons are negatively charged. So it's gaining electrons. Grr, gain electrons reduction. So the silver is being reduced. The way you would literally see this, by the way, you can run this. And this might be a little tough to see on your screen here, but this is just some copper wire right here in a copper chloride solution, in a silver chloride solution. So it's in this solution here. Over time, the silver actually plates out. And so this solid silver here comes out as a solid. You would see this actually occurring, that the silver would come out as a solid and it would sort of plate itself onto the copper wire. And so another example here we have what we could also classify as a combination reaction. We can see what's happening though is that the Na has an oxidation number of 0. So does the Cl. They're both in their natural state. But now Na is a +1 and Cl is a -1. So let's take a look at that. And so we have Na plus Cl2 to form 2 NaCls. There's our balancing. So Na is going from a state of 0 to a state of 1+. Cl2 is going from a state of 0 to then a 1-. And so our Na must be losing electrons because it's going from, it's becoming more positive, so it's losing electrons. The Cl is becoming more negative, so it must be gaining electrons. And again, I literally still write this out sometimes. Lose electrons, oxidation. My Na is becoming oxidized. My Cl is becoming reduced. And you can see that written out sort of in this form here. We have our Na is losing this 1 electron, and our Cl is picking some up. We can see it when we put together a sort of a Lewis diagram for this. That transfer is not always obvious, and we really don't need to go into more detail than that. In fact, let's just come back to this real quick. It's also important to note that whatever is being oxidized is also what we call the reducing agent. In other words, our sodium in this example is being oxidized. That means that the sodium causes the chlorine to become reduced. So since the sodium is causing that to happen on the chlorine, we say that sodium is also the reducing agent. Likewise, whatever is being reduced is the oxidizing, sorry for my handwriting, but is the oxidizing agent. Chlorine is being reduced. Chlorine is causing sodium to be oxidized. So chlorine is also known as the oxidizing agent. Just an example of an oxidation reaction, Statue of Liberty. Statue of Liberty absolutely came to us as copper. I mean, Statue of Liberty is copper. And so when it came to us, it was a copper color. And so we have Cu with its just zero charge, reacted with oxygen in the atmosphere, also with its zero, to form copper oxide. Now our Cu is a 2 plus and our O is a 2 minus. And so we can see that the Cu went from 0 to a 2 plus. And so, again, I really do this to keep it straight in my head, make sure I keep it straight in my head. The Cu is losing electrons, so the copper was oxidized. The oxygen went to a 2 minus. Oxygen was reduced. What color do you think copper oxide is? Sure enough, it's green. Any of you, and most of you are probably too young to remember this, but if you've grown up in Maine, I grew up right around the Augusta area. As I was growing up, the Capitol building always had a green dome. Same thing, it was a copper dome that became oxidized, turned green. Somewhere, I think it was right around the time that I was in grad school, so 15 years or so ago, I don't know if they redid the whole thing, if they took it off and they redid it, or if they just put new plating on, but they put new copper plating on. So that now is copper colored again. And we now know ways that we can prevent this from happening. Essentially, we put other metals in there too to control this oxidation or send this oxidation reduction reaction to a different place so it doesn't happen to whatever we want to stay copper colored. But this happened right where we can see it. If some of you are a little bit older and you've spent time around Augusta, maybe you remember that. But absolutely, as I was growing up, our Capitol building had a green dome on it, copper oxide. Another type of reaction is a combustion reaction. Combustion reactions essentially are burning. And so if we look at the combustion of a hydrocarbon, so here's a hydrocarbon here made up of just carbon and hydrogen. The other reactant in combustion reactions will always be O2. And here's another big key. The products of a combustion reaction, always, always, always CO2 and H2O. Always, always, always. But they're just another oxidation reduction reaction. We have you can see here. So this is another way to think of oxidation reduction. Oxidation increases our amount of oxygen on something, and reduction decreases the amount of oxygen. So we can see that our CH4 or our carbon is becoming oxidized, increasing the amount of oxygen. Our oxygen is becoming reduced, losing oxygen and increasing hydrogen. Another way to think of these reactions. Go ahead and let's go through these. Pause the video now and try to classify each of these reactions as combination, decomposition, single replacement, or double replacement. Pause the video now, see what you can do, and then we'll take a look at the answers. Hopefully for A, you got double replacement. B was a combination. C is a decomposition reaction. And D is a single replacement. If we're trying to classify reactions and we want to see if a reaction is oxidation reduction or not, we need to look at the different charges on things. And we need to see if our charges change. If they do, then it's an oxidation reduction reaction. And so for instance here, we can see in this reaction between chlorine and sodium bromide, we look through all of our charges and we see that Cl starts out as 0 in our reactant side, but now it's a -1 in our product side. So Cl is going from a 0 to a -1, electrons are being gained. Bromine, however, is going from a -1 to now 0, so electrons are being lost. And so we're changing charges here. Quite often, and this won't always hold true, but quite often, single replacement reactions are also oxidation reduction reactions. Whereas in a double replacement reaction, the charges don't change, and therefore most double replacement reactions are not also redox reactions. Something to keep in mind. Let's look at, in our last example, our last type of reaction, looking at some acid-base reactions and how antacids work. Antacids work where if you're, let's say it's a Friday night and you've been out having a little fun perhaps, and you top the night off with a couple good old greasy burritos. Wake up in the middle of the night and you're just burning right through here. Some good old heartburn. That's literally caused by acid rising up from your stomach and traveling up through your esophagus. Not fun. So stomach acid contains hydrochloric acid, quite concentrated too. And so that hydrochloric acid, though, is needed to begin digestion. I mean, we have concentrated stomach acids to start up our digestion process for us. But if it moves up, if it refluxes up, that's reflux and the cause of heartburn. And so we pop some Tums, pop some Rolaids, and that seems to relieve it. Take a look at what's happening. So milk of magnesia, I think it's the primary ingredient in Maalox, is pretty much just magnesium hydroxide. What we have here is an acid-base reaction, which we will look at in a later video, but it's just a simple double displacement reaction. The magnesium kicks out the hydrogen and then comes together with the chlorine. The hydrogen then comes together with the OH to form water. So just a very classic double displacement reaction going on. Active ingredient in Tums, most poppable antacids, is calcium carbonate. Same exact idea. A little bit different because we form H2CO3, which immediately breaks down into these, so don't worry too much about those details. But it essentially is just a double displacement reaction. And then hopefully our heartburn goes away. We go back to sleep and get up in the morning and have some Gatorade. Or I hear the new thing is Pedialyte, actually, to help out on a Saturday morning, perhaps. It was Gatorade back in my day. But anyway, that is our look through various reaction types. And I will leave us with saying, as always, stay classy, USM. And given this last little bit of conversation, stay safe as well.